Okay, I think this might be live. Let me check. Okay, it looks like it's good. Let me test the audio. Okay, we're live. Let me set this up. Okay, today I'm going to be reading this paper called "Were RNNs All We Needed?" It's by Leo Fang, Frederick Tung, Mohammed Osama Ahmed, and Joshua Bengio, and Hossein Jimir Sadeghi. Sorry if I mispronounced any of those names. This paper introduces a variant of RNNs that can be run in parallel pretty efficiently, and tries to propose an alternative to the transformer language model architecture. Let's read the abstract. The introduction of transformers in 2017 reshaped the landscape of deep learning. Originally proposed for sequence modeling, transformers have since achieved widespread success across various domains. However, the scalability limitations of transformers, particularly with respect to sequence length, that's important, sequence length causes the memory and compute usage of transformers to grow quadratically, because every token has to pay attention to every other token. And this has sparked renewed interest in novel recurrent models that are parallelizable during training, offer comparable performance, and scale more effectively. In this work, we revisit sequence modeling from a historical perspective, focusing on recurrent neural networks, RNNs, which dominated the field for 2 decades before the rise of transformers. Specifically, we examine LSTMs and GRUs. So these are 2 different kinds of recurrent neural networks. And maybe I could explain just a basic idea of the difference between a recurrent neural network and a transformer. So if you have some sequence of tokens, call it 1, 2, 3. Let's say 3 tokens. In language modeling, a model would take in some, let's say the first 2 tokens, and try to predict the next 3rd token. And the way that an RNN would do this would be by having some hidden state. You have some initial hidden state before you see the first token. And then after you see the first token, these are both inputs to the next state. The first token in the initial state, tokens to the next state, S1. And then the next token and the current state are inputs to the next state, S2. And then finally, we could use a separate set of layers to use S2 to try to predict what the next token 3 might be. And with a transformer, so let's call this RNN. Let's write that RNN. And then with a transformer, you could have the same sequence and the same kind of goal, to predict the third token from the first two. But instead, what you can do is if you're given these, you can produce each of these previous tokens. If we want to predict the third one, we could go from the second one. It can produce a query, a key, and a value. And the first one can produce a key and a value. It'll also produce a query, but we don't need the query yet. Let's see, text, key, and then we have value, inquiry. In order to find out the information from this last token, we can compute the similarity between this query and every other key. So this would be the first value in that row of the attention matrix and the second value. These are computed by taking the inner product of your key and your query. And in this row, you'll have the same query, but a different key. And then your output for this will be a function of the values in the attention matrix, in that row of the attention matrix. Let's call this output for token 2. Guess we should just make that clear where it's come from. This is an inner product. Let's say dot product. Or no, wait, this is a scalar. This is just a scalar product. Scalar. Yeah, each of these is a scalar, these A's. And it's used to scale up the value. And so we have another one here. And it takes in this value. And then you add these up. Whoa. And you get the output, which can be used to predict the next token. And here, since I'm only doing it for one token, it's hard to see, but this second token has to pay attention to every previous token and itself. So that means that whereas the RNN only needs to do one step of computation to get to the next prediction in generation, Transformer has to look back at every single one of these previous tokens in computing this attention matrix. I guess I should also add that there's a softmax somewhere in here. Yeah, that's good enough. Okay. Let's go back to this. And okay, I guess I should also say LSTM and GRU are types of RNNs. And we'll see that later. Okay, back here. We demonstrate that by simplifying these models, we can derive minimal versions, min LSTMs, and min GRUs. These are variants of LSTMs and GRUs that they propose. They say that use fewer parameters than traditional counterparts, are fully parallelizable during training. That's a big key, because in an RNN, you can't parallelize training. You have to walk back through every single one of these steps when trying to calculate your gradient. The state here depends on this state, which depends on this state, and then you need to go all the way back. And you can't efficiently do that with multiple tokens when you're predicting multiple tokens like this. Okay. And then point 3, it's achieve surprisingly competitive performance on a range of tasks, rivaling recent models, including transformers. So they say that these models are also give good benchmark results. Okay, since 1990s, recurrent neural networks such as long short-term memory (LSTM) networks and gated recurrent units (GRUs) have been go-to methods for sequence modeling tasks like machine translation and text generation. However, their inherently sequential nature, like I pointed out here, this is sequential, limits parallelization, made these models computationally inefficient and too slow to train on long sequences, common challenge in real-world applications. And then transformers suffer from quadratic computational complexity because every token has to pay attention to every other token. If you have n things paying attention to n other things, that's n squared. And then let me skip through this a little bit. There are different ideas to make these transformers more efficient. Say in this work, we revisit sequence modeling from a historical perspective, focusing on the RNNs. So they're going to retry to go back to RNNs and make some changes to the derivation and eventually come up with a presumably better model. Okay, so here's the review of RNNs. They say that LSTMs, this is how LSTMs work. So the hidden state, here these are, I call that S. They say, what's O? Let's see. Oh, the O is just a gate. Okay, so that's just a parameter, it sounds like. Or no. Oh, it's defined right here. It's defined as with a linear of x in the previous state. And an activation function. So this activation function is important to keep in mind because the fact that there is an activation function is part of the reason why it's hard to parallelize, as we'll see later. They define C as a weighted sum of F and F and I are also linear in the input and the hidden state, similar to O. And then we again have another one that's linear. This is the other weight for C. Let's see, it seems like everything is really dependent on the previous hidden state, which is, again, makes it really hard to parallelize. Okay. Let's see, here it says the gates I, F, and O control the flow of information through the LSTM. The input gate I determines how much of new information from a candidate cell C should be added to the cell state C. This is the new information. This is the previous C. Okay, and this is how you update it. Okay, the output gate determines what information the cell state should be hidden. Output as the hidden state H. Okay. And here says this function's sigmoid and tan H are used for scaling the values, ensuring the outputs do not explode or vanish during training. So again, this nonlinearity does break some of the ways to easily make it parallelizable. An LSTM module maintains both the cell state and a hidden state, and in total contains this number of parameters, okay, based on the hidden size and the input size. Okay. GRU says it's simplifying LSTM They introduced gated recurrent unit, which uses only 2 gates in a single hidden state. This is a simplification that has performed better. Here you can see that they only use one variable z for the weighting. And you have 1 minus z and z, so this adds up to 1. The total weight here is 1. So that prevents a lot of the exploding gradient problems, and also the fact that z is limited between 0 and 1. So the weights will also, 1 minus z and z will be limited between 0 and 1. And then they have this hidden state here that's also limited between being between -1 and 1 this time, because it's a tan H. Okay. GRU combines the forget gates and input gates into a single update gate Z. So you can see that this only uses 1 Z in this weighted sum. The other one uses F and I in the equivalent sum. Okay. Additionally, GRU removes LSTM's output gate and introduces a reset gate, which controls how much the past hidden state is used when computing the candidate hidden state H. So that basically rescales H, it looks like. R, yes. R just scales how much of the previous state you use. Okay. So this is the main introduction, or main thing that this paper introduces to these networks. Due to this limitation, the introduction of transformers revolutionized the field by replacing LSTMs and GRUs. Okay, and that's because it's parallelized during training. Got it. Doesn't need to backpropagate through time to train. Okay, the parallel scan algorithm is a parallel computation method for computing n prefix computations from n sequential data points via an associative operator. And they call this the operator with the symbol with a plus and a circle. The algorithm efficiently computes the sequence of prefix sums. Okay, I should probably pull out the whiteboard for this. This is if you combine everything up to k with that operator from the input sequence. Okay, so let's go here. Imagine, let's just say that that operator is a plus sign, and you have some sequence of inputs. Okay, you have some sequence of inputs. Let's call them. I should give them values like 1. Let's say this is actually the number 1. Then you have 2. 3. 3 and 4. You have these numbers 1, 2, 3, and 4. And a prefix sum would be something like you add up all of the previous numbers. I should just with 3 to make it simpler, but I guess 4 is good because the math works out well in the parallel form. Okay, so this is kind of messy, but hopefully I could get my point across. If you add up at the first token, you only add up the first token. At the second token, you add up the first 2 tokens. This would be 1 plus 2, which is just 3. And then here you'd have 1 plus 2 plus 3, which gives you 6. Then here you have 1 plus 2 plus 3 plus 4. Then you get 10. So this would be the prefix sum of these four numbers. But this is not an efficient way to do it, because here, after calculating the first one, I could reuse some of that computation, calculate the second one and the third one. Like, I don't have to add up 1 all these times, and then 2 all these times, and then 3. There's a way to do it where you only use each number once. So that would be, if I take these numbers, okay, this is a prefix sum, and then this is going to be the constant time update. So if I could now have hidden states. Let's color these in blue. So here the hidden state would just be the same as the sum, but you could have different numbers than the sum. But so we with this first say that it starts at 0, and then whenever you see a new number, you add it to your hidden state. So 0 plus 1 is equal to 1. And then we could say, take this value, which is just 1, and then we can add 2 to it. So we say 1 plus 2 equals 3. And then that's smaller. Now I have 3 here, and we have another 3. So we have 3 plus 3 equals 6. And then 6 plus 4 is going to be 10. So 6 plus 4 equals 10. So we end up getting the same result. We get 1, 3, 6, and 10. But instead of needing to have so many arrows here between all the numbers to add up all the inputs, we can instead go from this and just take in one number at a time and compute these along the way. And now, to do it in parallel, if you have a highly parallelized hardware such as a GPU or even a CPU with the right instruction set, it's parallel update. Parallel update is the easiest way to think about it is, first you could look at the cells that are next to each other. So you could say 1, 2, and 3, and 4. I could combine these. So let's get that. We get, it's a bit strange, but once you see it, it'll make sense. Okay. So we know that we need to add up all the previous numbers. So that means we just do it locally between every group of 2. We get this. Okay, here. So this is the same idea as up here, but just with the first 2. So, and then the second 2 have the same pattern. So we have 1, and then we have 1 plus 2 gives us 3. And this one just has 3. This one has 3 plus 4 is 7. Okay, so now we know that these tokens these ones are done. They don't have any other information to the left of them that they need. But these tokens here need the information that's to the left of them. They're all missing this 3 here. They're missing the information from the first 2 tokens. So what we can do is these ones can stay the same. Yeah, but we need to take the last one of this group. Let's actually make this clear how it's a group. Group them like this. Okay, we could take the last part of the group, which has all the information of everything in the group, and combine it with everything in this group. Okay, here, get this. So we get 3, we have to add the 3 to it. 7 plus 3 gives us 10. This 3 plus 3 gives us 6. And you could imagine extending this to even further sequences. So after this, if there were more things over here, like a 5 and a 6, and then they get an update. Like that. Why is this? Like this. 5, 6. Oh, it's the wrong arrow type. Okay. These can get the information. So these are the first in their group of 2 blocks. So let me make that clear. If we have, then we start grouping them making larger groups. We double the group size at every step. We first have groups of 2, now we have groups of 4. This one can receive, it's the first in its group of 4, so it doesn't need anything, just like this one didn't need any update here. But now we can take the last item of the 5, 11, yep. We take this last item here, this 10, and use our addition operator to take all its information into here and here. And we could go in further into this sequence, 15 and 21. And then over here, since this is the first in its group of 2, with 2 groups of 4, it doesn't need any updates. And this is our final result here. It's a lot of steps. It's actually slower than this constant time update in time complexity form. So this would be, so if there are n items here, this would take O of n time. Each item would take constant time to update, and we have n items. But in this one, we have n items, and then here we have 3 updates. And that 3 comes from the fact that we have effectively have to scale up, double it 3 times, which means that this can fit up to 8 tokens. You could have tokens here, up to 8. So the way that's represented in time complexity form is O of n log n. And the log means how many times you have to double it in this case. So here we have to double it 3 times to get 8. So this would be 3 times 8 in this case, because there are 3 update steps. This first one, second one, third one, and 8 items. Okay. So this is the prefix sum algorithm, and it works with any associative operator. And the associativity is important because we're assuming that you can take all the information and combine it on the left side and update it later with the information on the right side. So it means we could basically group all the information together into one new number, such as here this 10, and then aggregate it with the other data later. And addition is associative, so this works very well with sums, but we could see other types of associative operations in the future. And it talks about the same thing here, that you could do it in parallel with this product. This is just the same as what we've seen before, but replacing all of these with vectors, and then you could scale them up in some cases. Okay, methodology. We can see that the GRU's hidden state and LCM's hidden state recurrences resembled the vector formulation. In this section, we demonstrate that they're trainable via parallel scan, removing their previous state dependencies from the various gates. Okay, so now here, let me mark these in blue since these are hidden states. Here, imagine if we could aggregate all these states together to compute the next state, given some information in parallel. Then we wouldn't need to go all the way back to get all the information. Okay, building on this, we further simplify the RNNs by removing their constraints on the output range. So that means you no longer need to worry about bounding the values between -1 and 1. Combine these steps, we describe minimal versions of GRUs and LSTMs that are trainable in parallel. Okay, so the simpler one of these two is the min GRU, because GRU is a simplification of LSTM. Here, this is the same hidden state recurrence from earlier, and this can be done in parallel. First, you have to calculate this average. I guess this isn't an average. It's let me figure this out. This is an average because the weights here add up to 1. But what they do is they first do all the 1 minus z's, all the 1 minus z terms, to basically continually shrink this h. And then at the end, I believe they multiply by this, they introduce this term. Let me find it. Where are they? Here. Yeah, so first they keep on they keep on multiplying by this and adding. Oh no, actually, yeah. So they only have to multiply by the 1 minus z's, and the things that they add are already multiplied by z. So let's write this down. Okay. If you have okay. So z is going to be the weight, which is a function of the content. And let's see. Where do they introduce? Oh, b is going to be another projection of the content that represents how it's transformed. Okay. So you have a hidden state. Let's start with the recurrent form. The constant time update. And now we could actually introduce some numbers. Say they're just like 1 for now, maybe -1. Okay, 1. We could maybe have a 0 or something. And then a -1. And let's say these are the B values, which are just wait. So Z is the weighting. Where's the content? H is the hidden state. I guess H. Which one's X is the hidden state. Z and R. Oh, where's R in this? It's in H. HT. This H with a tilde. A, B, B. Wait, maybe the Z is definitely the weighting. I guess this is just the new content, yeah. Linear in the okay. This is gonna be, let's call it H tilde. Okay. This is here. I don't know how to write it like that. I don't know. Here. And this is H. And then okay. And then we have X somewhere that produces H, and it produces, where is it? H and Z. Z in maybe green. Or, I don't know, yellow. Okay. So we have Z here. It's just going to be, this is going to be between 0 and 1 because it's going through the sigmoid function. Let's just say they're like 0.5 here, maybe like math easy, like 0.2 and like 1. We can see what happens. Okay. So H should be initialized to 0. And then we multiply H by 1 minus Z. How should I write this? It's gonna be hard to draw. What's this? Okay. Okay, so how do I make this arrow curve? There. This is the weighting between H, the previous H, and the current H bar, or H tilde. So this is going to be, say this is going to be, you write it like this. So it's going to be 0.5 of H and 0.5 of H bar, because 1 minus 0.5 is 0.5. So that means we have 0.5 of the 1 and then another amount 0.5 of the 0. So the answer is going to be 0.5. Okay. And then we could do the similar thing here. This is going to be here. Okay, so now we only have 0.2 of this 0, and the rest is 0.8 of the 0.5. This is, so 0.8 of 0.5 is 0.4, and then there's no new content here in this h, so it's because it's 0. So we could just, this is 0.4, and then we could see how this works. This is, we have a -1 with weight 1. That means it's going to be all of it is going to be this new -1. And you have 0 is 1 minus 0, or 1 minus 1 is 0. You have 0 of the previous h. So we could actually just say this is -1. So you can see that these z's kind of interpolate between the previous h and the current h tilde. And so if it's 1, you get all of it, all of this, and then if it's 0, you get none of it, and you just keep the old value of h, and you could have amounts in between that. Okay. And the nice thing about this is that you can compute it in parallel. So let's see an example of that. This might take a little longer to get through, but parallel update. So here, the thing that they do in parallel, they call V. And okay, got it. V. Oh, okay, wait, here they removed the hidden state dependencies on H. So let me explain that. Here, Z is just a function of X, which means that it does not depend on H. Let's say X. This is used to compute all the Z's and H tildes, but we don't have to worry about the fact that, yeah, so this can be done in parallel because you just do a pointwise function, get from one X to a Z or an X to a H tilde. Draw this. And then, okay. Got it. Okay, min GRU. So now the parallel form of this, let's take same values. Maybe we should add another one to get this to look nice. But, yeah, let's do that. Okay. Let's add one with a 0. So just use the previous H. This won't matter. 1. Okay. So at the first step, we need to compute, where is it? These values of B and V. Okay, so here we kind of transform this again. V will start out as 0, I think. What is it? V. I guess we could just start it out as z times z times h tilde. Okay. It's gonna be a lot of colors, I guess, if I want to mark all these. Okay. Now let's just add this over here to make it clear that this is just basically does nothing. Then this goes to there and here. Okay. Now we can compute our V's. I copy this. I guess they call them A and B first, but let A. So A can be actually initialized as 0, I believe. Let's see. A. Or maybe I should skip that. Oh no, A is just 1 minus Z. Okay. That's the weight. Yes, okay. So let's get A. This is H tilde C. Okay. So we have A is going to be 1 minus Z. 0.5. Make A green. Wait, this is the 0.8. No, 0, 1. Okay, so A will keep track of how much of the previous group you will need. And say B will keep track of the current content of the token. How do I color? Out of colors. I'm gonna reuse blue for B because it is close to a hidden state. Okay, so B is initialized as, I think it's, maybe it should just be, B is just initialized as Z times H bar. Right? Okay. So this should be 0.5. Should be 0.16. No, H bar 0. So it's just 0. Yep. -1, and this is going to be 0. Okay, now we can start doing a prefix sum using two states now. So the update rule is that first let's update the A's. Or no, that's probably I better update the B's first to make this look better. Okay. So it looks like the B's get the next B, which is gonna be this V, I think. You add A times the previous. Okay. So let's start with this one. And then I guess we should also, let's copy all these over. Okay. Here we have A times, no. So let's say the previous one here. I guess, so since the previous is 0, we'll ignore it for now. And we'll just say that these two don't get updated. These are just like this. There's no previous, so you just copy the value over. And then for we can start grouping them. That's what we need to do. We need to group them into groups of 2. Let's make a little square around that. Okay. So that's right. Yes. And H. Okay. So okay. B in each group of 2. Let's first start with this. Each group of 2. Each group of 2 needs to update using all these values. Then this one from here to here. Or no, I guess it doesn't need this one. And then, yeah, it just needs these 3, I think. So it would be this A times this B. Yes. So this would be 0.5 times 0.5. Or no, maybe it's this B. Or this A. Yes. So it is this one. Since these 3 are needed. So you multiply this 0.5 by 0.8 like we did before, and then we add 0. Just like we did before. So this is going to be 0.4. Okay, this next one, we take -1 times 1 plus 0. -1 times 1 plus 0. That gives us -1. We already have the same sequences before, but that's just because this was a 1, I think. Or the fact that this was a -1. Wait, no, this is a 1. Yeah, the fact that this is a 1 means that it ignores all this. So maybe we could change that. Let's swap these around. Be a 0 and then a 1. That would be more interesting. So if I update that, and then, so this will be a more interesting example that way. Okay, 0 times H, then this is A is 1 minus Z, so it's gonna be 1, 0. Okay, so now they have a more interesting example. We get, okay, yep. Yeah, we got 0. No, wait, this is just 0 becomes 0. Okay. And then we have we need to multiply these two and then add this. 0 times 0 plus 1. Get 1. And then we see that if we compare these two values, first one's already fully updated. The second one is missing the information from the first two, which is this 0.4. And this and then we also need to update the weights, I believe. Let's see. No, I don't think we do in this formulation. Okay. Okay, yeah. Yeah, we don't need to. Okay. Now, do we? Wait. Looks like we don't, but maybe, wait. We might need to. Because, yeah, if this was something other than 0. Okay, let's actually make this even more interesting again. Here, it's gonna be half of 1 and half of 0.4. That'll be 0.7. Yeah. Okay. So if we make this example a little more complicated again, we get 0.5 times 1. This becomes 0.5. This becomes 0.5. Okay. Got it. Okay, so this is 0. We have 0 times 0.5 plus 0.5. Becomes 0.5. Okay, now I think we have to update the A's. Let me think. This is, this is also not a good example of the 1 here. But I guess I'll just run through this example anyways. Is it? Wait. Yeah, no, let's just make this, let's make this a 0.5 actually. I really want to illustrate this point. 0.5 of -1, 0.5 of -0.4, or 0.5 of -1, 0.5 of 0.4. It's negative. What's that? Negative 0.3. Yeah, should be right. And then if we get half of negative 0.3, let's change this to like 0.6 or something, make this math easy. Or no, wait, 0.5 or something. This gives us 0.1 here. Okay. Sorry with all these bad examples. I was trying to simplify the math, but it just didn't illustrate the right point. And then this needs to be negative 0.5, 0.25. Okay. So now we multiply these two. Is that right? Yeah, I think so. We multiply these two. Add this, we get 0. Yeah, okay, this is getting right, yeah. And then to get this one, we copy from the one above. And then here we have to update the A's. Oh, did I just close that? Here we go. So our A values have actually a much simpler update rule. They have to, you just multiply the A's together. All the previous A's get multiplied into the current one. So this would be like that. And then this. Okay, so we get half of 0.8. Am I doing this right? Yes. I think so. Okay. Now we take 0.5 stays the same. And then you multiply these two together. Get 0.25. Okay. So now we take we're done with this group level. We go on to the larger group level where we take this B and the last A, and let's introduce that over here into the next B. And this is the last step we need. Technically, we could compute the next A, but we don't actually need that for the output of the model. So we could just compute the B's here. Okay. Take our current value of B. We have to add it to, we actually don't need this A here. We don't need the previous A's. We need the current A's. Let's see, this is a B, this is a B, this is a A. We don't need the A. Okay. So we have the current B, the previous group's last B, and the current B's. We have to multiply those by these A's, I believe. Multiply the previous B's by the current A's. Yeah. So that gives us, okay, so here, let me get the current A. It's this. Current A times previous B is 0. Wait, no. Current. Did I get this math? Yeah, I got it. Current. It's the current B. No, current A times the previous B. Current A is 0.5, previous B is 0.4. So that gives us 0.2 plus. That gives us 0.2. And then we have to add the 0.5 here. Why is this not? Yeah, we have to add the 0.5 to this 0.5 times this 0.4. That gives us the negative 0.3 that we wanted in the answer. We do a similar thing here. We take, we already have that arrow. We take the previous B, multiply it by the current A. So previous B times current A, that would be 0.1. And then add it to this 0. We have 0.1 plus 0 gives us 0.1. And that gives us the final answer. This is a bit complicated to draw out, but I hope it's clear how this works. This is basically an extension of the prefix sum here. This only has one type of state. This one has two states that one multiplies the next one and one adds a weighted version of the previous. So then we copy in the previous B's here because they don't have any previous information to introduce. And then we get our final sequence that matches in a parallel form. So each of these groups can be done in parallel on a GPU or similar hardware. You could run these in parallel, and then you could run even larger steps in parallel. You could run these in parallel, which makes it a lot faster. Okay. And then I guess for the output, they just they say what their output is. I think the output is just a linear function of the h's. Let's see. Min GRU. Here we go. They don't really say. I guess we could just assume that this is how they transform it. I think where would they say that? I'm gonna skip over min LSTM because it's I think it's pretty similar. A little more complicated. Yeah, with the different updates. But it's very similar. They don't say. They only say that they calculate the hidden states. But I'm gonna assume that the output of this type of neuron would be some function of the hidden state. Okay. Here are their results. It seems like. We compare the minimal versions with their traditional counterparts and modern sequence models. So look at the runtime as a function of sequence length. And this is, I believe, a runtime measured how long it takes to do a single token, because this looks like it's constant per token and linear per token. I think. Let's see. Yeah, it's for training. Yeah. So it's how long it takes to train on a new token, I believe. So the speed up is linear as well, since going from linear to constant is a linear difference. And then the memory scales better. Looks like, yeah. Okay. It says they're efficient. At test time, recurrent sequence models are typically rolled out sequentially, which makes inference relatively inefficient. The main bottleneck lies in the training, which can't be done parallel for these basic RNNs. Okay, they say how much faster it can be during runtime, how much less memory it can use, and the fact that so the fact that the h's and the z's are no longer a function of the previous h, like they're only computed from the x's, it does mean the function is less expressive. So it could make the performance worse, but typically that's mitigated by the fact that it's much faster to train. And apparently you could increase the number of layers because there's increased stability. And then they compare it to other efficient parallelizable RNN models such as H3, Hyena, Mamba, S4. And their method outperforms it in some ways. Okay, I'm gonna skip through this. Okay, this is the main thing. They consider language modeling task. This would be, again, using these outputs as predictions for the next token. Let's see. And they say transformers were significantly slower, requiring 2.5 times more training steps than their min GRU. So that's a big speed up, and it's also be a big inference difference to this. I could skip over this maybe. Conclusion. In this work, we revisited the history of sequence modeling, focusing on traditional RNNs, specifically LSTMs and GRUs, which dominated the field for 2 decades before the rise of transformer models. We demonstrated that we can enable parallel training of RNNs by removing their gates dependencies on the previous states. So the inputs to this recurrence or this prefix sum algorithm are only a function of the input to the input tokens. And this gives them full parallelizability during training. And then they provide implementations in plain PyTorch requiring only a few lines of code. That's useful. Let's see. Limitations, references. Let me see if I can find that that PyTorch implementation here. Sequential mode, where it is. Where's the actual PyTorch? Just an algorithm. Okay. Where's this parallel? Is that even a PyTorch function? Parallel scan. Say the weights are from 0 to 1 with the sigmoid, linear of x, and they've another linear to produce these h tildes. And then, do they say what the parallel scan function is? Here we go. Here's the parallel scan. It's like they compute it in log space. I guess yeah, the coefficients should be tracked in log space, yeah, because they range from 0 to 1, so you can take the log of them and when you do it, and I guess instead of multiplying each of the a's in this update, where you let me actually put this out here. Instead of multiplying 0.5 by 0.8 here, you could add the logs and then normalize. Seems like, yeah. Yep, there's basically adding them here and then normalizing. Then I guess the values are also in log space, so they can do that as well. Instead of needing to multiply the previous value by the, I guess, I mean, here I have negative values, but if you made all the values positive, you would be able to take the log and then just add them together instead of needing to multiply it by the content it needs. Multiply the weight A by the content B. Okay. And then yeah, here. Okay, they just yeah. So I mean, also it's faster to run a addition on most hardware than multiplication. But I mean, most GPUs are bottlenecked by memory bandwidth, not really the like if you look at an H100, 100 flops by precision. If you look at for the how long it takes to do operations at each precision, like the time it takes to do a multiplication and addition, especially once you get down to FP8 cores. Where can I find that information? I've seen this before. There was it on this page? Specifications? Maybe this. Or I guess, yeah, I mean, I guess the fact is that it doesn't really matter if it's addition or multiplication or if it's float or int. Like you get the same number of flops for the same amount of memory. Like if you have 8 bits per scalar, you literally get the same between float and int. And then same thing with bfloat, fp16. Like the main constraint here is how fast the memory can be accessed, not how fast you could actually multiply the numbers or add them. But again, addition should be faster than multiplication. So that is helpful to convert to log space for that reason and for the stability of the training and everything. Okay. So let me make sure I've covered everything. Let's say I covered this. And covered that. I think that's all for this paper. If you like this, I might do more videos like this. I really liked this paper because it introduced a really cool idea here with this parallel scan to efficiently compute in parallel and stuff. But it'd be interesting to see what other kinds of associative operators could be useful in training these language models, instead of just this one where you scale and add. So yeah, that's pretty much it for this paper. Again, I might make more of these videos, so if there's interest, that'd be good. Yeah.